Lecture on gravity. We're going to focus mostly on the middle guy here, Isaac Newton. But really, this story of gravity that I want to tell you is kind of a metaphor for the history of science itself. So let me just spend a couple minutes talking about the various roles that these three physics luminaries have in explaining gravity to us. So on the far left, we have Kepler. Now, Kepler uh, really is the first kind of systematic study of gravity before we even knew that we were studying gravity, right? And so this is kind of like the early steps of science when you're doing experiments and you're just gathering data and you're looking for trends in data, right? So Kepler specifically was looking at the data that had been gathered over a number of years about the position of the planets and the sun and the moon, and basically use that data to try to find trends and sort of like underlying truths, if you will, that were mathematical in nature, right? Which he did successfully, and I'll talk a little bit about his three laws of planetary motion. And that's kind of like the first step of science in general, right? You gather data and you look for trends. Now, the second stage of the story is our middle guy, Isaac Newton, right? Three laws of motion and all that good stuff. He comes up with not just an explanation of the trends in data, right? But what he's doing is like, step number two in science, which is he's finding a universal function, right? He's finding a relationship between values that then explain the phenomenon, right? And so that's what we think of as gravity now is why are these trends in the data of the planetary positions over time is because there is a universal force called gravity, and that's the explanatory mechanism, right? Now, at this point, the story is pretty complete, except for perhaps a philosophical one, which even Isaac Newton um, uh, said at the time, which is he could explain Kepler's observations and make further predictions and explain a lot of other things with his concept of universal gravity. But the question that he did not have the answer to is what is gravity? Like, how does it work? This action at a distance. How does the sun reach out 93 million miles and pull inwards on the Earth? He didn't have sort of a underlying mechanism, right? So you've got the step one with Kepler, which is finding trends in data and finding mathematical relationships. Step number two of coming up with a kind of a universal explanatory law. And then it takes Einstein here several hundred years later. So Kepler's like late 1500s, early 1600s. Newton is late 1600s, and Albert Einstein's early 1900s. Einstein comes up with an explanation for what this gravity is, right? And the explanation is just is amazing. It's so unintuitive and crazy, and yet well verified. And so he, kind of at long last, puts to bed this question of like what gravity is, and it turns out the answer is the curvature of space-time by mass. Now there are plenty of scientists that say the story isn't over, right? This is the way science. Every time we think we have all the questions answered, we find some kind of little nook or cranny in the latest data that indicates that something is not completely explained, and that is happening today in astrophysics. There are two kind of deep mysteries, dark matter and dark energy, which are not completely satisfactorily answered with Einstein's general relativity. However, it continues to be the best explanation that we have for the phenomena that we see today. All right, so most of the problem sets and most of the physics that you need to understand are actually the Newtonian ones. So I'm just going to briefly talk about Kepler. And then when I talk about Einstein, really your job would be to sort of like kind of get that there is this, really complicated essential truth. And I also want you to really kind of understand that it's not just an idea, but that it's an important idea and that it's experimentally verified. So that's kind of all I need you to get out of the last portion of this lecture with general relativity. So what did Kepler come up with? These are the three trends that he found in the data, and all of these then get explained by universal gravity, right? But let's talk about the trends that he extracted. His first law was that planets move in elliptical orbits with the sun at one foci. Now, this is a really big deal at the time. In the late 1500s, most people are still believing that the universe is centered on planet Earth, and they believe that things, to the extent they do move, they're moving in perfect circles because that's what perfection is. And so this is two blows at once, right? Not circles, but ellipses, and we're not at the middle, but the sun is. Kepler's second law, this is what he found in the data, is that, and I have a graphic of it on the right, if you wait like, say, 1 week in a planet's motion or something, and then you fill in the shaded area, like the slice of the pie, if you do that week at various points in its orbit, you'll shade in different sized pie slices because the planet is moving faster or slower, right? It moves slow when it's close, and it moves quickly when it's close to the sun, and it moves very slowly when it's far away. And that changing in speed is offset by the distance just such that the areas swept out in the equal time periods are equal. Now, this will be explained by Newton by coming up with a precise formula for the velocity as a function of distance, right? And then the third law is also related to this idea that the farther away things are, the slower they go. And that is comparing one planet to another. The time it takes for the planet to go all the way around, so-called orbital period, so that's like 365 days for the Earth, that time squared divided by the average distance to the sun, cubed, right? So the t squared over r cubed, that every single planet around the sun has the exact same ratio, right? So it turns out these Kepler's laws are manifestations of gravity, and so it should not surprise you to find out that they are obeyed by any set of objects that's orbiting a common central object. Like, so for instance, all the satellites of Earth, including the moon and all the man-made ones, they obey Kepler's laws around the Earth, right? Or all the many dozens and dozens of moons of Jupiter around Jupiter, they're obeying Kepler's laws with respect to Jupiter. So the story for Newton really is one of him actually understanding motion more so than forces, right? He's thinking about that force that's pulling us towards the Earth, gravity. He's also the first person to actually understand how circular motion works, right? That you need that centripetal force that pulls you in towards the center of a circle in order to constantly change your direction. And so he's thinking about gravity, and he's thinking about the fact that the moon executes a circular orbit around the Earth. So that means the moon must have an inwardly directed force. And then he kind of has this aha moment where he's like, what if that inwardly directed force on the moon is the same as the inwardly directed force that I call gravity, or that, gives objects their weight. And so out of this, he comes up with this law of universal gravity. And this is what it looks like. So in his proposal, and this is, good enough to explain 99% of everything we observe in the universe, good enough to get, rocket ships to the moon. Any two objects, right? So it's not a function of planets, right? Any two objects that have mass, that's M1 and M2, the two interacting objects, right? Will experience a force between them, an attractive force. That's what we call gravity. And it's equal to the product of those two masses, right? So M1 times M2, divided by the distance between them squared, right? And so, and then the capital G is a universal constant that just kind of like calibrates what kilograms squared over meters squared, how that translates into newtons. So it's in effect measuring how strong gravity is in our sort of Earth-based metric units, right? And if you look at this number, the universal gravitational constant, it's extremely tiny, right? 6.67 times 10 to the minus 11th. And that is why if you just have a couple chairs sitting in the room, yes, they do experience gravitational attraction towards each other, but they will not slide across the floor towards each other because that force is so weak that it cannot overcome basically the friction on the floor. So there are experiments you can do, in your lab and stuff like that to measure this force, but you have to be pretty careful about it because this is such a weak force. And one of the videos I'm going to link is the first such, and still to this day, one of the best experiments to measure this universal constant in a laboratory setting between two known masses, right? And that was performed just after Newton published his work by another British scientist, Cavendish. And so I'll stop talking about that because the video does a really good job of explaining it. 1 over r squared is a really interesting thing. So Newton he didn't have a set of data to base this equation off of, right? This just came out of sort of like his deep understanding of math and geometry and science, because there wasn't a set of sort of like gravitational forces and distances and masses, until Cavendish did his experiment, it was really kind of not known what these values would be. But he was pretty confident in his proposal because being proportional to both masses just makes sense because mass is the source of the gravity. But I wanted to spend a second on r squared. So any fool could basically say, oh, it's going to be divided by the distance because as two objects get farther and farther apart, one would expect the force between them to get weaker. But Newton is not an average guy. He doesn't say, oh, it's 1 over r, or 1 over r cubed, or 1 over r to the x, right? He says specifically 1 over r squared. And his logic for that, I want to explain to you, is if you imagine embedding the mass, like this is a picture of, say, an imaginary Earth with a sphere around it, right? It should not matter where you're located on that sphere at a distance r from it. You should experience the same attractive force. In other words, right, there's no preferred directions in space. And so as you get farther and farther away from Earth or any mass, the reason why the force is getting smaller and smaller is because you're occupying a smaller and smaller fraction of that ever-increasing spherical surface area, right? And the surface area of a sphere is 4 pi r squared. So the reason why it's 1 over r squared is really because it's 1 over 4 pi r squared, and the 4 pi just gets pulled into the constant. And so actually any spherically symmetric force like electricity, for example, one proton pulling in an electron also doesn't care about the distance. You will find 1 over r squared laws in those situations for the same reason. Just want to point out the right way to measure r here, right? If you want to just pause the video and try to choose one. So the explanation here is if you think about symmetry and Newton's third law, really kind of the only thing that makes sense is letter C, right? It's going to be the center of one mass to the center of the other. Right? The other solutions are not symmetric. Now, I want to talk about something in science because as you layer on a new theory, so when Newton proposes universal gravity, that's got to be backwards compatible with Kepler's 3 laws of planetary motion. And then when Einstein proposes general relativity, that's got to be backwards compatible with Isaac Newton, right? So this idea is called the correspondence principle, right? If you're going to come up with a new and better and more robust theory, then it needs to explain and be shown to be compatible with, or even sort of reduce under those simple situations, 2 previous laws that you know and know to be correct. So let's talk about our simplified version of gravity that we first learned, which is little m times little g, right? And this is a point of confusion. Let's make sure we don't confuse these. Little g and capital G are both there for gravity, but they're completely different things, right? Capital G is the universal gravitational constant. It is a fixed number. It's one of the cosmic constants of the universe. It's that very small 6.67 times 10 to the minus 11th. Little g is talking about traditionally the gravitational field that we experience here on the surface of planet Earth, right? And it could be generalizable to other planets and stuff like that, but it is location dependent. And it is a value that reflects the gravitational field from an object. And so let me just show you mathematically how you would make them the same, right? So we're taking our functional definition of little g, and that we get our weight by multiplying our mass by the gravitational field that we are standing in. But that also should be the same as Newton's universal gravitational equation, right? So I'm m2, I'm standing on the surface of Earth. It's the entire mass of the Earth. It's the m1 that's attracting me. And the distance from my center to the center of the Earth is about the radius of the Earth. So if you put all those objects in there, you can solve for little g, and you find out that this is the formula for the gravitational field, right? So, which in a free fall situation can give you the acceleration in free fall. But the gravitational field in general, right, is capital G times the mass of the object that you want to measure the gravitational field from, divided by the distance from it squared. Now, that means if you do that, I think one of the homework problems has you calculate that, you will find that the gravitational field from the Earth extends and falls off, like 1 over r squared from the surface of the planet. It's not like these astronauts, when they go up into orbit, are suddenly in a 0G environment, right? So that's a real misnomer to say that they're weightless or that they're experiencing 0G. I mean, I guess that technically they are experiencing it and they feel weightless, but it's not because of lack of gravity, right? It's because they're in constant free fall, right? They're not experiencing a normal force, which, as we know from previous work, like the elevator problems, we know that's how you actually experience your weight. And so they are weightless no more than you are. When you trip and fall before you hit the ground, right, you're just as weightless during that falling as the astronauts are. The trick is, of course, the astronauts are falling constantly. So this gravitational field is an explanation for how gravity is transmitted from one place to another, right? So before Einstein came along, but post Newton, people started thinking about this little g as actually being where all the action is, right? So that is the explanation, if you like, the classical explanation of how the Earth knows that the sun is out there, right? Obviously, the Earth doesn't know the sun is out there, but if you imagine this big blue circle on the left as being the sun, you can imagine using that formula, capital G m over r squared, just based on the mass of the sun. And that's going to set up a gravitational field in all of space around it, right? So when you're close to it, you get these big red arrows because the value for little g for the sun is big. Then you get a little bit further away, and the arrows are a little bit smaller because the r squared is making it a smaller and smaller value, and so on and so forth. And so the way we think about gravity interacting in a classical way is that you put a mass in the universe, and it puts out a gravitational field and tags every point in space with a little g value, if you will, right? A gravitational field is called a vector field, technically. And then when you put a second object in there, like you put the Earth over here where this black arrow is, the Earth doesn't have to know anything about the blue sphere. The Earth is sitting in that object's vector field and just responds to the local value, right? And this is the idea of a field, right? People think about all of forces, actually. This is the paradigm for all of forces, right? Electricity works the same way. Magnetism works the same way. You have a source that creates a field around it, and then the second object is sitting in that field and actually interacts with the field. So now we're in a situation where we can just calculate little g for these astronauts that are in space. So you can actually use the formula, plug in the numbers. For r, their r value is only slightly larger than the radius of the Earth because they're not that far up, which of course is an indication that you're not going to find a big difference. So if you want, you could pause here and run the calculation to see if you're correct. Here's my calculation for it. Instead of 9.8, you get 8.9 newtons per kilogram. So that is definitely not zero, right? That's nowhere close to zero. It's only slightly less than the 9.8 that you and I are experiencing all the time. And that's good because they need that gravitational field to keep them in orbit, right? So let's put it all together. Let's go back to the origins of this. You know, Newton was thinking about circular motion and gravity. So let's put it all together. If we want to explain an orbit algebraically, this is what we do. We say, I have a centripetal force because I'm going in circular motion. You can do any orbiting object. So this picture is the Earth going around the sun. You could do the moon going around the Earth, a satellite going around the Earth, you know, a moon of Jupiter around Jupiter. It will still be the same kind of idea. If you're undergoing circular motion, no matter the nature of that circular motion, you need an inward force, a so-called centripetal force. In this case, that's supplied by gravity. So here is universal gravity, according to Newton. And on the right-hand side, a centripetal acceleration, we already know from our previous work, is replaced by your speed squared over r, right? So your orbital speed. So this is the balancing act. This is the formula that tells you how fast you need to go, right? And that's your tangential speed in order to maintain an orbit at that distance. Right? And so you can simplify this because the m2 is the same as this m, and this r is the same as that r, and you get a nice kind of elegant formula for orbital velocity. It turns out it's only due to two things. The orbital velocity you need is the mass of the central object and the distance you are from the center of it. Right? And this is how NASA and other agencies determine how fast they need to launch satellites in order to put them into orbit around the Earth. And of course, this is the equation that explains Kepler's second and third laws. You know, why is it the farther away you go, the slower the speed is? Well, it's because you have the same capital G and the same capital M, but you have a bigger r, which is going to make the whole velocity goes down. So the velocity is decreasing like 1 over the square root of r. Right? Just comes from simplifying universal gravity and circular motion. So here's the work, right? For Kepler's third law, Kepler could find the trend. He could tell you that r cubed and t squared have the same constant proportionality, right? So that everyone in orbit around the sun has the same t squared over r cubed ratio. But Newton can do you one better and tell you exactly what that ratio is, right? And that ratio is just a function basically of the mass of the central object. And that's why everybody in orbit around the sun has the same t squared over r cubed ratio, is because it's the mass of the sun that's driving that relationship. And so you can actually use this relationship, and people do use this relationship, to figure out what the mass of a distant object is, right? So when people ask you in astronomy, like, how do they know what the mass of the sun is? This is how they know. They measure the t and the r of an object in orbit around it, and from there they estimate the mass of the central object. If you see something through your telescopes and nothing's in orbit around it, well, then you don't have a really good way of calculating it, right? They can put some parameters around it, and they can make some guesses based on other objects. But if you really want to know the mass of something without being able to weigh it, you have to find something in orbit around it and apply. This is called Newton's version of Kepler's third law. And you'll definitely need this for one of the homework problems. So this is orbital motion, right? This is something Newton understood right away as soon as he understood circular motion, right? Is that if you take a parabola and you make it large enough, eventually that parabola will circle in on itself. And that's just a question of launching it with enough speed, right? And that speed you can determine by this equation, right? It turns out to be tens of thousands of miles per hour, like 15,000 or 17,000 miles per hour to get something in orbit around the Earth, which is why it doesn't happen easily. Okay, so final chapter here, and the most interesting one I would have to say is that Einstein is not actually explicitly thinking about gravity at first. He's thinking about motion and relative motion and the fact that two observers, whether they would agree or disagree when they're looking at a motion. He's been thinking about this since 1905 when he came up with special relativity, where he realized that there's some really interesting things about how the universe works if you just accept the idea that two different inertial observers, that is constant velocity observers, should agree about the physics of how the universe works, right, which is a basic tenet of physics. But it turns out, like, since those velocities can be very, very different, in order to accommodate that rule, right, that inertial observers should come up with the same law of physics, you have to combine space and time in ways that people had never done before Einstein. And so he's thinking about space and time, and he's thinking about relative observers, and so he wants to apply it to the accelerating reference frame. And so what he does, eventually he publishes this in 1916, is his central theme for general relativity is the equivalence principle about accelerating objects, right? So he says that if you are standing on Earth, the downward pull of gravity, which can result in a downward acceleration, right, if you fall freely, should be completely indistinguishable in every way to an actual acceleration through space, right? So if you're in a sort of a black box out in space and someone accelerates you up at 9.8 meters per second squared, that normal force on your feet in the left picture here should be the same as the normal force on your feet in the right-hand picture. And so his tenet, his equivalence principle here, which leads to all the conclusions of general relativity, is that these are equivalent. In other words, that the gravitational field is simply just an acceleration. Or another way of thinking about it is that the m that you use in Newton's universal gravity, right, the mass that gives you that creates a gravitational field or that responds to someone else's gravitational field, that is the same value as the m that you use in F equals ma. But that's actually two completely conceptually different things, right? Mass, as I first introduced it to you with F equals ma, is a property of your inertia, which talks about your resistance to changes in motion, which doesn't say anything about creating a gravitational field or responding to it, but it turns out it is the same, right? And so Einstein said, well, if you follow that through carefully, right, the picture on the left, your m is acting inertially, and the picture on the right, your m is acting gravitationally. So another way of saying that these accelerations are the same is that the masses are the same, gravitational mass and inertial mass, which is something that scientists have been using and thinking were the same for a long time, but nobody had really kind of followed it all the way through. And so he is thinking about this for over 10 years, right? And he comes up with a series of what he calls Gedanken experiments, which are thought experiments, to try to figure out, what kind of behavior you would see. So here is the first one, and the most important one, is imagine the two observers again, and now they're going to do an experiment, right? So there should be no experiment that they can do to distinguish these two cases. Remember, observer on the left is actually accelerating upwards through space, right, using his inertial mass, and observer B is stationary on planet Earth using his gravitational mass. So inside of this box, if you cut a small hole and allow a beam of light to come in, right, as that beam of light crosses across the room, observer A is actually accelerating upward, and so therefore the light will actually hit the wall at a lower point. Right? Does that make sense to everybody? The time it spends traversing the room itself is moving in the upward direction here, And so it's going to hit some delta h, which is a function of course, how fast you're accelerating, and a function of how wide the room is and the speed of light, right? But here's the surprising thing, is that if this is true for observer A, and it certainly would be true, then it must be true on observer B. Otherwise, there would be an experiment you could do to tell the two situations apart, and they wouldn't be identical. And so what this means is that in a stationary box, in a gravitational field, when you do the same experiment, the light should fall by the same amount, right? Which you could explain if you said, oh, well, light is falling under the influence of gravity. It's going into free fall during gravity. But light has no mass. So when you go back to universal gravity, right, the m2 for a beam of light is 0. And so Newton would predict no free fall for light. In fact, most people believe that if you shine light, it travels in a straight path. And Einstein is saying, well, if that's true, that light would go in a straight path, then these two pictures are not equivalent, which means that your inertial mass and your gravitational mass are not the same, and that these accelerations are entirely different. And the fact is that people know that these masses are the same, right? And it turns out that this picture on the right is actually what's happening. When you turn on your flashlight, the beam of light starts to fall just like a rock at 9.8 meters per second squared. You've just never noticed it. Right? Let's do a quick kinematics on why maybe you've never noticed it. Let's say the room is 100 meters wide, and you shine the flashlight, right? So you look up the speed of light. There it is, very big number, 3 times 10 to the 8th meters per second. Horizontal velocity is constant, so I'm just going to divide my 100 meters by my speed of light to find the time. It turns out it takes the light 3 times 3.3 times 10 to the minus 7th seconds, right? So very short period of time. And now the drop distance we would get from the delta y equation, right? I've got a typo here. I've lost the t, but I did do the calculation correctly. Vyt minus 1/2 at squared. It turns out that the light in that small fraction of a second is going to drop 0.5 times 10 to the minus 12th meters. Okay, this is why no one has ever noticed the free fall of light. It's like the baseball pitcher throwing the baseball, at 100 miles per hour. It drops so little that people have the illusion it's going in a straight line. Well, the light, of course, is super fast, and so the illusion that it's not falling is even more so. But it is dropping. So what's the explanation? Why does light drop in a gravitational field? What is a gravitational field, right? The question that made Newton feel so unresolved. And Einstein's answer is that the inertia of an object and the gravitational field of an object are one and the same. What it is when you put the mass into the universe, he's imagining a space-time fabric, right? He's already been imagining a space-time fabric that you have to deal with if you are talking about observers making scientific measurements. You can't separate out space and time, right? It's a 4-dimensional space-time fabric. And what he's saying mass does is it warps the space-time fabric. So what you can imagine, you can't really imagine warping 4-dimensional space-time because you can't even picture 4 dimensions. We're just simple creatures. So here's a 2D limit, a simplified version. And so this is just a useful metaphor. It's not actually what's going on because, like I said, it's a 4-dimensional problem. You put a mass in, it's going to make a dent like this in the space-time fabric. And it's that dent that makes it hard to change the motion of the object, right? It resists changes in speed and direction because it's created this dent in the space-time fabric. And the larger the mass is, the bigger the dent is. And that's the inertia explanation. And the gravity explanation is, well, look, I bent space-time around it. So all these lines that are supposed to be straight are now curved. And so when light is trying to follow the shortest path between 2 points, it is not going to be a straight line anymore. And so that is Einstein's explanation of what gravity is, which is just amazing if you think about it, right? The reason why things are falling is because they're just trying to hold on to their inertia. It's the space-time around the Earth that is actually warped. And so as they try to hold their position, as you march forward through time, you wind up seeing this object drop towards the floor, right? So orbits, right, would be explaining that a lot of science museums will have like a large porcelain bowl, and you'll like shoot marble in there, and you'll see that marble go round and round and round. And of course, it's actually got some friction, and so in the science museum, it'll roll down and fall through a hole in the bottom. But in outer space, there's no friction, and so that's why the planets and satellites can just keep going around and around forever. All right, let me talk about 4 experiments. When he published this paper, nobody was like, "Oh, you're a genius." Everybody was like, "Well, if this is right, you better, have some experiments for us to do." And he did. He suggested number 2, and he explained number 1 in his paper. So people took him seriously, and people have been testing general relativity ever since, and it has passed every single test put to it. Right. So this crazy idea of the warping of space and time is experimentally valid, verified many, many times over. The one that made him famous is number 2. Um, Number 1 was in the paper. There was the elliptical path of Mercury. In fact, all the elliptical paths of all the planets are precessing. That is, they're changing their orientation over time, and that is well understood. But it could not be explained with Newtonian gravity for the planet Mercury. People could explain it for the other planets, but Mercury, as it turns out, Einstein showed it's so far down into the bowl created by the sun that you cannot pretend like space-time is flat anymore. And so Newtonian gravity G m1 m2 over r squared can't explain this precession rate, but Einstein could with his mathematics of general relativity. Here's the experiment that he proposed, which then this is when Einstein, 1919, that's when Einstein became a world famous celebrity, right? He was already famous within the physics community since 1905, but it wasn't until 1919 that he became like a cultural phenom, right? And so even though he did a lot of his work when he was much younger, that's why he became so famous with his, kind of white crazy hair and all that kind of stuff. Here's what he proposed. He said, look, if the sun is actually creating a dent in the space-time fabric, then when light from a distant star comes out in a straight line, it will actually get diverted by that curved space-time, right? And then when it comes out of the bowl and goes into our telescope here on Earth or your eyeball, you will see it coming in on a trajectory that makes you think it came from somewhere else, right? So if you think that things come in straight lines, which is what people do, then you'll trace that light backwards and you'll see the star in the wrong place. So he said, take a star that you know, that's well studied, and you know exactly where it is, and wait for it to go behind the sun when you normally wouldn't be able to see it, and then look for it off to the side like this, right? Because he can calculate this angle deviation with his formulas. Now, the problem with this, and the reason why people didn't do it in 1916, is you can't look towards the sun. You can't point your telescope towards the sun and see a star behind it because there's too much light coming from the sun. So in 1919, there was a solar eclipse, and Sir Arthur Eddington actually, I think he commissioned a boat to go into the path of totality and took this measurement and did find that a star that was known to be here appeared to be over here at exactly the location as predicted by general relativity. Now, some people were still not convinced because they're like, well, you could explain perhaps the light not traveling in straight paths by things other than distorting space and time, right? So people wanted to test those 2 criteria separately. And so number 3 is the testing of the warping of space, and number 4 is the testing of the warping of time. So let me explain those very briefly. They both happened here locally in Massachusetts. So in 1960, laser technology was good enough that they could shine a laser beam up a stairwell, basically, I think in the Harvard Physics Building, and measure the wavelength of that very precise light at the different stories. And if indeed planet Earth's gravitational field is stretching out the fabric of space, then that wavelength of light as it travels through space will also appear to change wavelengths. And it did, right? And the wavelength changed by exactly what was predicted by general relativity. Couldn't be done until 1960 because the laser technology and the wavelength measuring devices weren't good enough until then. Now, to measure time was even harder, and so that had to wait for the invention of atomic clocks. But in, I'm sorry, I was thinking of a different experiment with atomic clocks that was related to special relativity. For general relativity, this is how they measured the time delay. So the strong gravitational field of the sun causes time to tick off more slowly as you get closer. That's how the seconds get stretched out. As you get closer to the surface of the Earth, you're actually aging more slowly than you are if you're on the top of a mountain. But the effect is really hard to measure, right? Because it's very small. And so this is what MIT has a radio telescope out. It's called the Haystack Observatory. It's out in Westford, Mass. And in 1966, they used that very large radio telescope to do a pretty cool experiment where they beamed a radio beam at Mars when Mars was roughly on the other side of the sun, and then they listened for the echo when it bounced back, right? So this distance between Earth and Mars is well known, And the speed of radio waves, of course, is a frequency of light, so that's the speed of light, is also well known. And so you can just double this distance, divide by the speed of light, and you get the time delay for the echo. Now, if Einstein is correct, then the beam of light will actually spend more time than predicted near the sun, because time itself travels more slowly then, ticks off more slowly. And general relativity can tell you exactly what that time delay should be. And of course, when they listened for the echo, it did come in late by exactly the time delays predicted by general relativity. Nowadays, this warping of space-time is so intrinsic to our understanding of the universe that astronomers use it all the time. So astronomers on Earth will frequently use this effect called gravitational lensing, where they'll look at an object that is too far away for their telescopes to actually see, and but they will look at it through the lens created in the space-time by the presence of a large mass, like an entire galaxy, right? So an entire galaxy, of course, is warping space-time quite a bit. And so these beams of light, it's like the 1919 experiment all over again, right? These beams of light that would normally go in a straight line and never get intercepted by Earth get curved around, right? Refocused, if you will. And so the telescope actually sees several different images of this object on either side of the galaxy and can stitch them together and make a new image. After he published his paper, somebody else said, hey, I used your equations to prove the existence of something crazy, which eventually became known as a black hole. And Einstein thought this object was so crazy. And of course, back in 1920 or so, there was no evidence that these things existed. And so Einstein actually worried that there was something wrong with his theory. But it turned out his theory was just better than he was. I mean, he came up with this idea of the warping of space-time, but he couldn't predict all of the consequences. And one of the consequences is if you focus a mass tight enough, then you can imagine making the dent in the fabric of space-time eventually go basically vertical. And what does it mean to have a dent that's vertical inside? It means something falls in and never comes out, right? So even light would go in here and never come back out. And the term black hole was coined somewhat disparagingly, and then it stuck, right? There are all other kinds of terms that were batted around, but this is the one that survived. And so now these objects are called black holes. And astrophysicists did think of a way that you could actually squeeze that much mass in there. Certain stars, if they're large enough when they die, they could collapse in on themselves and get a high enough concentration of mass to create these conditions for a black hole. And in the 1960s, they started discovering black holes. They're very hard to find because of, obviously, you can't look for light coming from them. But what you can do is you can look for something in orbit around it, right? Here is data. Over here is the 1992, and you'll see it will tick off in months. These are a whole bunch of stars. Every point of light is a supermassive star larger than our sun in the center of our Milky Way galaxy. And watch what patterns they're executing, right? So if you look towards the center here, you will see that you have very, very large stars, which over the course of just a few years are executing an ellipse. Watch, they'll trace it for you here. They're executing an ellipse around nothing, right? Look at that. That is an entire star executing what looks like a planetary orbit around nothing. So you can calculate how much mass you would need in there, and it turns out to be a super massive black hole. So it is effects like this, until quite recently, these were the only ways we had of detecting black holes. Now, we have some very fancy techniques, and we can look at gravitational lensing around a black hole and actually image an individual black hole. Also recently, just a few years ago, another consequence from general relativity is if the fabric of space-time, right, as indicated here by this blue graph paper, if it is warping due to gravity, then you can imagine, just like putting your hand on the surface of water and moving your hand around, you can create waves and ripples. You can actually create ripples in the fabric of space-time itself, something known as gravitational waves. But back in the day, people really, you could do calculations on how big these waves would be, and the energy is so small, right, and the effect is so tiny that really people had no inkling that it would be possible to do. And still around the maybe 1970s or so, 1980s, a few people in the astrophysics community thought they might be able to technologically get the job done. And they built the world's most sensitive apparatus, right? I've got a link to a video that talks about just how hard of a scientific task this was. And they did build this object, and it did detect gravitational waves in 2015. And now we're building more and more of them, and we're detecting more and more gravitational waves. And so yet another 100 years later, you're still getting new data coming in supporting Einstein's view that general relativity is the correct theory. Okay, thank you.